And then let's talk a little bit about the PBL scheme. So, you know, the planetary boundary layer have its height varying during the diurnal cycle. So when in daytime, the sun heats up the land, and then convection will occur. And then there will be a lot of convection and turbulence in daytime from ground level to about 1,000 kilometer height. For desert, for very hot days, it will be even higher. So a lot of turbulence here, and we call it a mixing process. So we have the planetary boundary layer height going higher in daytime. And then in the evening, the night cool down. And then there will be temperature inversion that the land surface is cooler than the atmosphere, and then it will form a stable layer without convection. And the land, what happens on the land is actually driving these changes in a daily cycle. So the stable layer will slowly grow to be thicker, and what remain higher than it is called the residual mixed layer. And then not long, and then day starts again, and the sunshine on the land again, and then convection starts to build up again. Okay, so this PBL scheme is trying to model these phenomena without simulating it computationally. And you will see a variable called PBL height, which is very useful. And for the vertical depth from ground to the PBL height, the PBL scheme will be working there to try to give a formulation that help the whole simulation to be correct. Okay, and then about 1/10 of the height nearest to the ground, it is called the surface layer of the atmosphere. Okay, and that part will be modeled by this surface layer scheme. So the choice of the PBL scheme and the surface scheme have to be paired to work with each other. So some features very obvious is that in daytime, if you analyze the potential temperature, you will often see a streak like this. So near the ground, the soil is hot, so it is giving heat flux from the soil to the surface layer of the atmosphere. And then you will see this is not straight, this is tilted this way. Because the land surface is hotter than the surface just adjacent to it. So in this area, it drives the air to go up. So it drives convection here. And then in this range of vertical height, it is called the mixed layer. The turbulence is very free. Where is the figure? Okay, it's very free. And then basically the mixing is very homogeneous. So you will see that in terms of potential temperature, it is mostly constant here because the mixing is well done. And then near the top of the PBL height, you will see that the upper is starting to be cooler than the lower. So convection pretty decelerate here. And then here will be the tropopause, some vertical height like that. So this is very patterns that you can easily recognize in daytime. And then all other variables are in accordance with the stage of the atmosphere in daytime, and they are like this. And then at night time, this is reality. It will, in reality, not really vertically strict, but have some slope. And then at night time, you will see that the ground cools faster, and then the temperature of the air above it is even higher. So you see the curve tilt in this way. So this is a stable boundary layer. And then this is the resident layer that still have some mixing. So in the YSU scheme, it has some mathematical formulation like this. If you're interested with the paper and search for slides. And then they have a model of some mathematical terms called KM. So that theory is also called K profile because it imposes a profile on this K. The profile is like this. In the YSU scheme, this K always has this shape. And it has some mathematical formula like this, which results in this shape. This H is the PBL height. So after it has a mathematical model of it, it has to regulate the atmospheric simulation because as you have seen, the vertical layers are very thin. Oh, I should lecture one. Lecture one. Where is the figure? Okay. The vertical layers are usually very thin. And then the horizontally it is usually wider. So if we only do the part of the simulation of the resolved variable, something will be missing. The turbulence, the effect of turbulence will be missing. So in this scheme, it uses this mathematical formulation and then adjust the simulation by introducing the tendency of momentum and heat calculated by it in this way. And then for the YSU scheme, there is also something called non-local mixing terms because the land is heterogeneous. Say, I have some reading on paragliding. The guys say that when you are playing paragliding in the sky, you look at the land surface, very often there are forests, but if you see there are some rocks, some bare land, and if the day is very sunny, actually it is not homogeneous. The bare land or the rocks will be hotter than the forest. And then there will be updraft from the very hot area of the land like this. So you will see that this updraft is very powerful. It goes across many vertical layers. So this K profile scheme works on only adjacent layers because it is something related to run something run C here. It is the difference in the vertical height of adjacent layers. So this is the so-called local terms, and it cannot do a good things if phenomena like this powerful updraft is actually occurring in reality. So in the YSU formulation, there is also some non-local missing here. Non-local means across many vertical layers, okay? So they have these things in the YSU formulation according to the K profile. And the other choice, MYNN, do it in another way. it does not impose the shrink of this K like this. It uses prognostic variables to model it. That is, there are terms for this radioid tensor. They group some terms, and then they write a formula run something run T, say the TKE, the rate of change of TKE a long time, and give it some formulation. You may read that MYNN paper. And also for there are different so-called closure order of their formulation. The simplest one may be just have a prognostic formulation for the TKE. And for higher order MYNN schemes, they may have some more time derivative formulation for the heat flux and also the momentum flux. So this is an example that different scientists use different approaches to make a mathematical model for important physics phenomena, and then offer them as open source software integrated to the NWP model for you to choose. Okay, I will not go into further details into this. So okay, some more practical things. So we have done some experiments, right, for Hong Kong. And this is Kings Park. So we extract the simulation data and then interpolate it to this location, and then look into the vertical, the y-axis is the vertical height relative to the 1.0 means the PBL height. And then this is the variable we look into. This is potential temperature. So the experiments also show that in daytime, okay, this is an afternoon, the potential temperature is quite in correspondence with the theory. So the ground is hotter, and a little bit upper, it is becoming cooler. So convection is triggered here. And then going up, this is the mixing layer, more or less like constant potential temperature. And then go up to the PBL height, convection cannot go further up. So it becomes cooler and cooler and no more mixing. And for horizontal wind, we will see that the wind speed is about 6 meters per second or something in this range of height. And then for water vapor mixing ratio, you will see that near the ground it is the moist, and then going up and up, it becomes drier and drier, just what you experience when you in a flight, and then in the aeroplane, you will feel that the air is quite dry. Okay, and other slides on the resulting K from the experiment. They are also having this shape in accordance to the formulation. Okay, this shape from the formulation, from the theory, and then this shape from experiment. So this is also afternoon. In daytime, the PBL height is about higher than 1 kilometer. And then this is for heat, and this is for momentum, similar profile. Okay, the figure is here. And it also shows the PBL schemes take care of these vertical layers, and the surface layer scheme take care of this, about 1/10 of the height. And then for night time, you will see that the ground is no more hotter. And this is kind of residual mixing layer. And then the wind is, in Hong Kong, it's still 6 and something meters per second in our experiment. And then mixing ratio. And then at night time, the PBL heights become lower. Okay, so only 500 meters in our experiment. And then this figure is important if you are using numerical simulations for renewable energy, especially the wind power. So you will see this pattern. The x-axis is the local time, so this is daytime. In daytime, near the surface, the wind speed actually become higher because there are turbulence. But if you go into higher altitude, like this altitude is for wind power application, you will see that at night, there will be even higher wind speed to give it wind power. But in daytime, the wind speed usually decrease. And then when sun goes down, and then the wind speed usually goes up again. So wind speed and height at night, it is like this. In daytime, it is like this. And we have tried some simulation, we find similar thing. The wind speed at night can be higher than the wind speed in daytime. So you can imagine what happened in daytime, like this, and this, when you are near the surface, this turbulence is driving some random wind, and then the horizontal wind speed can be higher than nighttime. But for higher height at nighttime, there may be nocturnal low-level jets. So wind speed can be higher at nighttime at higher altitude. So these are interesting things that we have some experience. So this is the end of the lectures.